about so-called carrier multiplication phenomenon, which is the process by which, by absorbing a single photon, we can't tangle electron hole pair, but multiple electron hole pairs. And of course, this process would be extremely useful in a number of technologies, from photovoltaics and photocatalysis to nonlinear optics and lasing. But at the same time, as I'll show you, this effect exhibits a lot of interesting physics, quite muted my presentation. So it happens that so far the process of high efficiency carrier multiplication has been observed in a single class of nanoscale materials, which are nanocrystal quantum dots. So these are nanoscale particles, okay, with sizes from roughly 20 angstrom to 200 angstrom. And nanocrystalline regime appears as intermediate regime between cluster molecules on one side, bulk semiconductors on the other side. And the interesting feature of this regime is the strong dependence of nanoparticle properties on their dimensions. This is due to the quantum size effect. And one of the consequences of the quantum size effect is in size-dependent energies, specifically the size-dependent energy gap. Now you have a bulk contribution to the gap, and then explicitly this quantum confinement term, which scales as 1 over r squared for spherical particles. Okay? The smaller the size, the wider the energy gap. And for nanocrystals, which we are working with, extremely small particles, this confinement term is not a small correction to the energy gap. It can be comparable to the bulk energy gap, or can even be greater. Okay? And of course, having tunable energies and tunable energy gap are very important for having tunable materials in emission and absorption. And you can think about applying this effect in photovoltaics by trying to match the absorption spectrum of your material to the solar radiation spectrum. This is the example of tunable absorption spectra for lead selenide nanocrystals of different sizes. If you look at the absorption onset, you can see that I can tune it by changing the size of the particles across mid-infrared and near-infrared spectral energies. And if you talk to photovoltaic people, they will tell you this is an extremely useful capability for optimizing the performance of photovoltaic structures. Okay, let's talk about the normal photoabsorption process, which observed traditionally in semiconductor molecular systems, and then compared to the regime where we have carrier multiplication. So normally, you absorb a single photon, and in response, you obtain a single electron hole pair. Even if your photon energy is much greater than the energy gap, then this excess energy is going to be dissipated very rapidly as heat with very efficient electron-photon interactions, which in bulk semiconductors are characterized by very short time constants, tens of femtoseconds. Okay, now imagine the situation where you have very strong carrier-carrier interactions, which can compete with electron-photon interactions. In this case, you can think about the energy transfer phenomenon, in which the excess energy of your initially excited electron is transferred to the valence band electron. And if this excess energy is greater than the energy gap, then this electron, secondary electron, is re-excited across the energy gap. As a result, you absorb a single photon, but you produce two electron hole pairs. And this effect has been known since 50s. It occurs in bulk semiconductors due to so-called impactization. The problem is only that it's not extremely efficient in the range of visible and infrared energies, which are relevant to the conversion of solar energy into electricity. It turns out that the situation changes very dramatically if we go to the regime of small nanoscale particles. And this is the plot of quantum efficiency for converting photons into charges as a function of the pumped photon energy normalized by the energy gap. And you can see that using these nanocrystals, we can generate 7 excitons per single absorbed photon, which correspond to the 700% quantum efficiency. Okay? So it's not that this number is very large. What is interesting, that this number corresponds to the ultimate multiplicity which you can produce for this pumped photon energy according to energy conservation. You cannot generate more than 7, and you generate 7. Okay? As I already said, the effect is not new. First report about quantum efficiencies which are greater than unity appeared in 1957, this paper by Kors, who studied germanium-based photodiode structures, and he noticed that above certain threshold energy, about 2.5 electron volt, the quantum efficiency started to exceed unity, and then it grew linear with increasing palm photon energy, eventually reaching about 107%. Okay? And since then, a lot of work has been done with regard to both experiment and theory of this effect, and several general trends have been established for this process, the process of impact ionization, trend related to the activation threshold for this process, and trends related to so-called electron hole creation energy. So this is the energy which is lost by the ionizing particle, an electron or a hole, during a single impact ionization event. And if you have these plots of quantum efficiency versus palm photon energy, it can be derived simply as inverse slope of this linear dependence. The steeper the slope, the smaller the electron hole creation energy, and the ultimate minimum value is, of course, energy gap. So you need at least the energy gap in order to produce a secondary electron. Okay, what actually turns out that for a large number of studied semiconductors, the electron hole creation energy obeys very simple rule. It's so-called free energy rule. So it's close to 3 energy gaps, so 3 times as high as required by energy conservation. Okay, as a result of this high energy, actually the thresholds for activating this effect are also quite high. So it's about 4 energy gaps or greater, while again the theoretical threshold would be 2 energy gaps. So these numbers are large, and that's why the efficiency of carrier multiplication and the rate of solar energy spectrum is not high. Okay? So now, how nanocrystals can help us? Turns out there is a number of reasons to believe that the effect of multi-electron production can be enhanced in nanocrystals, and one of the reasons was actually pointed out in this paper by Nozick in 2002, who considered the change in the intraband relaxation mechanism as you go from the bulk to nanoscale systems. So one signature of nanocrystals, as other quantum dot systems, is the development of the discrete energy structures. Okay? And that has been expected to slow down intraband relaxation due to the photon bottleneck. Okay? In the models which consider impact ionization as a mechanism by which carrier multiplication occurs, impact ionization competes with intraband relaxation. If interband relaxation is suppressed, that shifts the balance in this competition in favor of impact ionization. As a result, we may expect enhancement in the carrier multiplication efficiencies. Okay, right now, I will tell you later, the mechanism for carrier multiplication in nanocrystals still a subject of big debate. So we don't know how it works exactly, but the fact is the efficiencies for carrier multiplication are indeed greatly enhanced in the case of nanoscale particles. This is obvious from this simple comparison, where I show quantum efficiency as a function of the palm photon energy divided by the energy gap for lead selenide bulk crystals, and the data actually were measured in 1958 at Bell Labs by Smith and Dutton. And these are our data, very recent data obtained for lead selenide and lead sulfide nanocrystals, and you see 2 very pronounced differences. So we have the reduction in the activation threshold, which goes from approximately 5 or 6 energy gaps to below 3 energy gaps. Okay, what is most important, actually the slope becomes much higher. In the case of the bulk slope, we can tell that the electron hole creation energy is about 5 energy gaps. Based on the slope, which we observed from nanocrystals, the electron hole creation energy is precisely energy gap or smaller. Okay, so this is the ultimate limit allowed by energy conservation using these nanoscale particles. We are getting efficiencies which are only limited by conservation of energy. All right. So we don't know how it works exactly. But something which is likely is important is very strong carrier-carrier coupling, which is required in order to produce this effect. And carrier-carrier coulombic coupling is greatly enhanced in nanocrystals compared to the bulk. And the reason is, actually there are several reasons for that. One reason, of course, is a very close proximity between two interacting charges when you confine them within a nanoscopic volume of a nanocrystal. The second reason is reduced dielectric screening. The electric field penetrates outside the nanocrystals. Therefore, it sees actually a low dielectric constant, which is characterized the dielectric environment in the nanocrystal, and that leads to effective increase of Coulomb interactions. And some experimental indications that carrier-carrier interactions are enhanced in nanocrystals. We obtained them back maybe in the end of 90s, in the beginning of 2000, when we started multi-excitonic dynamics in nanocrystals. So if you excite a single exciton in the nanocrystal, the intrinsic decay channel is radiative recombination, and it's characterized by relatively slow time constants, about 20 nanosecond in cadmium selenide nanocrystals, and about 1 microsecond, or even longer for lead selenide nanocrystals. Okay, now you're exciting a second electron-hole pair. You potentially open another recombination channel in which the electron-hole recombination energy is not released as a photon, but instead is transferred either to the electron or to the hole, to so-called recombination. In bulk semiconductors, is a low efficiency effect. For example, never been observed experimentally in bulk cadmium selenide, but turns out, as you go to the regime of nanocrystals, this effect becomes extremely efficient, leading to very fast recombination constants from tens to hundreds of picoseconds. And these time constants are several orders of magnitude faster than characteristic times of the radiative decay. This is a very illustrative example, okay, which shows that the process, which simply not observed in bulk semiconductors, starts to play a dominant role in the case of nanocrystalline system, and that indicates this great enhancement in carrier-carrier coupling, which I was talking about. So not only these experiments provide this indication that Coulomb coupling is very strong in the nanocrystalline system, but it also gives us a tool which we can use in order to detect multi-excitons in the case when we are producing them by carrier multiplication. Okay? We're going to distinguish between single excitons and bi-excitons based on very significant difference in their recombination dynamics. Okay? We're going to perform a transient absorption experiment in which we first excite a nanocrystal with a short palm pulse, which has a tunable energy, and we're going to probe the population dynamics in nanocrystals by monitoring absorption changes at the energy of the lowest energy transition. Okay? And let's consider the situation where using large photon energies, which we can potentially produce carrier multiplication. So the photon energy are sufficient in order to produce multi-excitons without violating energy conservation. In this regime, we may expect that in a portion of nanocrystals, we obtain bi-excitons in addition to single excitons. And now we have these two sub-ensembles which show distantly different recombination behavior. Single excitons decay very slow, very radiative processes on nanosecond to microsecond time scales, while bi-excitons should produce very fast decay due to other recombinations on picosecond times called constants. So, first of all, just the appearance, the development of the fast component in transient absorption traces, when we use very low pump intensities at which we cannot create bi-excitons directly, will signal us that yes, we start producing multi-excitons via carrier multiplication. And furthermore, we can use now these dynamical traces in order to quantify the efficiency of the effect without any additional reference measurements. And the idea is the following. So we have bi-excitons initially, but then we know that they decay very rapidly, whereas the recombination producing at the end single excitons. Okay? So now we know at the end of the fast decay, in all photoexcited nanocrystals, we only have single excitons. So we have a well-defined exciton multiplicity at the end. It's 1. Now we can use the slow background as a single exciton scale bar in order to quantify multiplicity right after photoexcitation. We can simply divide the amplitude of the signal by this height of the slow single excitonic background. In this way, we obtain quantum efficiency and initial multiplicity.
How does stand out to depends on radius?
Okay, it scales with the radius. The smaller the radius, the faster decay. And this is 1 over RQ. Okay. And these are real data. Okay. So this is what we published in 2004. We're looking in this case at lead selenide nanocrystals using very low quantum densities. We're going to scan palm photon energy from low energies when we cannot produce multi-excitons based just on energy conservation. And you see 165 energy gap below 2 energy gaps, and we observe slow single excitonic decay. Now we increase the palm photon energy. Okay, and at palm photon energy, for example, 3.14, we already observe fast component. As we increase the palm photon energy, the amplitude of the pump of the fast component grows. And based now on this amplitude, for this black trace, we can determine that the quantum efficiency achieved in this experiment was 220. So we produce 2.2 excitons per each absorbed photon. Okay, now you can ask me the question. So how can I be sure that these multi-excitons are not produced with sequential absorption of multiple photons from the same pulse? Okay, I can tell you, first of course, we're using low pump intensity. But what we also did recently, we actually analyzed the distribution of populations produced in the case when we don't have carrier multiplication and when we have carrier multiplication. Let's look at the usual process of creating multi-excitons at high pump intensities. In this case, the average number of excitons per nanocrystal determined by the product or the pump fluence and the absorption cross-section. But of course, we're going to have the distribution of multiplicities. Okay? And distribution of multiplicities is supposed to follow Poisson statistics. Okay? Now, we introduce additional quantity. Actually, I mentioned it already. This is the average multiplicity of photoexcited excitons. And this quantity is actually different from the average number of excitons because average multiplicity is the average number of excitons per photoexcited nanocrystal. It can be related very easily to this number by this relation. So you have average number of excitons per nanocrystal divided by the fraction of photoexcited nanocrystal. And using Poisson distribution, you can calculate this value and check if actually obeys correct limits. In the limit of low pump intensity, the average number of excitons per nanocrystals goes to 0, but the average multiplicity as defined by this relationship goes to 1. So by definition, it cannot be smaller than 1. Okay, now let's consider the experimental situation where we cannot see carrier multiplication. So our pump photon energy is below the activation threshold, and I'll show you in a few slides the activation threshold for carrier multiplication in lead selenide nanocrystal is approximately 3 energy gap. So we're below this value, our photon energy is 2.5 energy gap. Okay, we're going now at a fixed photon energy, change the pump intensity, and these are the traces which we are obtaining in this case. So we're using relatively high intensities here, where on average we generate 1 exciton per nanocrystal, but of course, because of Poisson statistics, we are producing multi-excitons, and you can see this fast decay component due to this fraction of nanocrystals which have multi-excitons. Okay? Now I'm going to reduce the pump intensity, what's happening to the fast component. Of course, the amplitude of the fast component goes down until at very low pump intensities where we excite on average 0.05 nanocrystal, electron-hole pairs per nanocrystal, we don't see any fast component, so we are not producing multi-exciton anymore. Now, based on these amplitudes of the fast and slow component, we derive multiplicity, as I explained in the previous slide, and we are plotting this data shown by these blue symbols. Okay? Now, plot this line, which is derived just using Poissonian statistics, and I see exact correspondence. So it's essentially something what I expect for the Poissonian system. I get it, so no surprises. Multi-excitons in this case are generated with the usual process of absorbing multiple photons from the same pulse. Okay, now the only change I'm going to do in my experiments is the pump photon energy. Now I'm going to buff the threshold for carrier multiplication. I'm going to 3.3 energy gap. Now I'm allowing production of multi-exciton with this new process. And again, I'm looking at the traces, and you see now what's happening at very low intensities. I still see fast component indicating that I'm still producing multi-excitons. Again, I'm quantifying this data, plotting my results, and compare that with what I would expect for the case of the Poissonian ensemble, and I see this very dramatic difference. I'm dealing now with non-Poissonian system, implying that multi-excitons in this case are generated with some new process. Okay, it's not absorption of multiple photons and something different. Okay, and the illustrative result, as I reduce the pump fluence, I see that in the limit of the zero pump intensities, I have non-unity multiplicity. That tells me that multi-excitons are generated at zero pump fluences. Okay? That implies immediately that can be only explained if they are generated by single photons. Okay? So in this particular case, after proving that we are producing multi-excitons from single photons, we can quantify the efficiency. In this case, it's 1.3. Okay? So this is what we published in 2004, and since then, several people complained. So transient absorption is not the correct method for observing multi-excitons. Is it observed by some other means? And recently we actually published a paper where we reported observation of carrier multiplication using a different experimental technique that would be time-resolved photoluminescence. Okay? And these are the data which actually are obtained for a different type of nanocrystals. In this case, we're going to look at cadmium selenide nanocrystals. What I'm doing here, I'm comparing the transient absorption and photoluminescence dynamics side by side. So all these traces are taken under the same pump conditions. And first, I'm looking at dynamics, which I recorded with low pump photon energies and in low fluences. In both cases, I observed the slow single excitonic dynamics. So they are seen in both transient absorption and photoluminescence. Now I change the excitation condition. I keep excitation fluence very low. So on average, I'm producing 0.1 exciton per nanocrystal. I simply increase the pump photon energy, so it's approximately 3 energy gaps, and I generate fast component. And the transient absorption signal, I generate fast component. The photoluminescence signal, okay, so the carrier multiplication, which is seen in transient absorption, is seen exactly in the same way in photoluminescent decks.
Room temperature measurements?
Huh?
Is it room temperature or low temperature?
Everything what I'm talking about is room temperature. All right, now we can use these fast traces.
Sorry, what is the binding energy of the...
We're going to talk about that.
Okay.
Okay. Now I'm going just to compare efficiencies derived based on the transient absorption photoluminescence data. I'm plotting here, so black symbols, squares, these are transient absorption data, and these red circles are photoluminescence data, and you see pretty good correspondence. Okay, so basically, it's an important experiment which actually validates all the conclusions which we earlier made based on transient absorption study. The carrier multiplication is seen also in photoluminescence. Okay, the interesting actually feature of photoluminescence measurements, now we can use these measurements in order to observe spectral signatures of carrier multiplication. That addresses your question regarding the binding energy of the biexciton. All right, so we know that in nanocrystals we have very strong carrier interaction. As a result, the biexciton energy is going to be lower than twice the single exciton energy by the value which is determined the exciton-exciton interaction strength. As a result of this difference, the emission wavelength for biexcitons is going to be redshifted with respect to the emission wavelength for single excitons. Okay, but this again value which is determined by the strength of exciton-exciton coupling. And we studied in our earlier studies, you can look up this paper, directly the exciton-exciton interaction strength in cadmium selenide nanocrystal as a function of the size. You can see, depending on the size, it's different, but it can be as large as 30-something MeV. This is very significant interaction energy. And now what we're going to do, we will try to detect this biexcitonic shift in the case when we're exciting our samples in the regime of carrier multiplication. So we're going to look at time-resolved spectra of emission. And of course, at long delay after excitation, when all multi-excitons decay via recombination, we're going to see a single exciton emission spectrum. This is the spectrum here, which is taken at 3 nanoseconds after excitation, this black line. Now, we're going to go to time zero and perform experiment under 2 excitation conditions. First, low pump photon energy, no carrier multiplication, but high intensity. Okay, we detect this red shifted spectrum, which corresponds to the emission from biexcitons. Okay, now again, we're changing condition. We're dropping the pump fluence to very, very low numbers. We're exciting just 1 nanocrystal out of 1,000. So the average number of excitons per nanocrystal is 0.001, but we're increasing the pump photon energy to approximately free energy gap, and we see we recover the bi-excitonic spectrum, which is observed when we're exciting multi-excitons, bi-excitons directly. So it's very interesting results. So it provides us with a direct proof. So we see emission in this case arising from the bi-excitons, but bi-excitons in this case are produced with carrier multiplication. All right. So I was talking about our initial observation of 220% quantum efficiencies for converting photons into charges. We reported them in 2004 and 2005. Nozick and co-workers reproduced these results, and they actually reported higher quantum efficiency, up to 300%. The question now, what is the ultimate limit on the quantum efficiencies which can be produced using carrier multiplication nanocrystal? The answer is, of course, that the ultimate limit is determined by energy conservation. So you cannot produce more excitons than is allowed by the ratio of the pump photon energy and the energy gap. If you use just this energy conservation consideration, you can obtain the staircase of ultimate efficiency, so the ideal efficiencies. So if your photon energy is between 1 and 2, the energy gap, you can only generate 1 exciton. If your photon energy is between 2 and 3, you can generate 2 excitons. Between 3 and 4, 3, and so on and so forth. Okay? So you cannot generate fractions of excitons. All right, recently we tried to see how close we can approach this ideal dependence for quantum efficiencies using very high pump photon energies, in the case of less solid nanocrystals, up to 7-point energy gaps. So the point is right here. So according to energy conservation for this photon energy, we can only expect the production of 7 excitons, no more. Okay, these are the results. So it's again dynamical traces. So we start with low pump photon energies. And when we increase the pump photon energies, and we see that there is this fast component which becomes progressively faster, and then it develops in a very sharp peak. If we take the amplitude of this signal at time 0 divided by this slow single excitonic background, we're getting value of 7. Okay, so we expect, according to energy conservation, obtain 7 excitons. And we did have in our crystals 7 excitons. It's interesting to look actually how this data develop as we increase the pump photon energy, which is shown here. Based just on energy conservation, we can activate the effect at 2 energy gaps, but it's not happening. The onset is delayed to approximately 3 energy gap, but then we observe a very fast growth in the efficiency with a slope, which is actually slightly greater than 100% per energy gap. That's why eventually we're hitting this energy conservation staircase right here. Okay? And of course, we expect some more interesting stuff happening at high spectral energy, something what we're working on right now. Okay, so now you can ask me, so why
one state saturates at exactly 8 excitons?
Okay, so this is actually just direct consequence of the band structure in less solid nanocrystals. So the minimum, it's a direct gap semiconductor, but the minimum of conduction valence band are not at the gamma point, they're at the L point. You have 4 minima, plus 2-fold spin degeneracy, 2 multiplied by 4, we get 8. So essentially, we can put in the lowest energy state 8 carriers. All right, so you may ask me the question, why we are not seeing the lowest possible threshold of 2 energy? Okay, so we know that the reason for having the threshold in bulk semiconductors is a combined requirement of energy and momentum conservation. So we're having relaxation and momentum conservation in the crystals. Why we're not seeing 2 EG? And my answer would be that in addition to energy conservation, still we have to observe selection rules. Specifically, we have to observe optical selection rules. Okay, and I'm going to illustrate this idea using bulk semiconductor arguments, but they can be easily extended to the case of nanocrystals. Okay, in the case of bulk semiconductors, optical absorption from the valence to the conduction band occurs vertically in the K space. Okay, that implies that the distribution of the excess energy of the photon above the energy gap is controlled by the electron and hole masses. In the case of lead selenide, we have a very peculiar situation where electron and hole masses are nearly identical, and that tells me that this excess energy is distributed between the electron and the hole electron. Okay? Now I'm going to apply energy conservation. In order to promote the electron from the valence band to the conduction band, the excess energy of either the electron or the hole have to be at least energy gap. Okay? And that immediately explains me why the observed threshold is 3 energy gap, because at the threshold, the energy of the electron is energy gap. Based on the symmetry between conduction and valence band, it tells me that the energy of the hole is also energy gap. Plus I have the energy gap which separates the valence from the conduction band. Energy gap plus energy gap plus energy gap, 3 energy gap. Okay? And the general expression is shown here. So this is, according to these considerations, how the threshold for Carrier multiplication is going to be controlled. It tells me also now how I can try to reduce this threshold, which would be important, of course, in order to improve the performance of materials, nanoscale materials, for voltaics application, to use a larger portion of the source spectrum if the threshold for activating this effect is lower. Okay, so what I need to do in order to reduce the threshold, I need to break the symmetry between the valence and conduction band. So I need to use the materials which have significant difference between electron and hole masses. And one such material is cadmium selenide, for example, where electrons are approximately 5 times larger than holes. In this case, I expect a reduction of the threshold. So the threshold would approach the ultimate 2G limit. Okay, let's look at the experiment. As actually I showed already some data for cadmium selenide nanocrystals. Okay, again, these are transient absorption or time-resolved photoluminescence study based on the amplitude of this fast component. I derive efficiency, I plot this efficiency here. And again, as in the case of flat selenide nanocrystals, they show linear dependence above a certain threshold, but the threshold now, as you can see, dropped down to 2.5 energy gap. And this is the comparison with what we have in flat selenide nanocrystals. So indeed, the threshold dropped in the case when we have asymmetry between the conduction and the valence band. What is actually interesting, if you look at these data sets, again, you think about the electron hole creation energy, which is determined by the slope of these quantum efficiency curves. You can see that the electron hole creation energy is very close in both of these materials, and this is a very interesting result. Because lead selenide and cadmium selenide are very different with regard to electronic structures, dielectric properties, carrier relaxation behavior. And what it tells me, so most likely this process is very universal in the case of nanoscale semiconductor particles. So it's general in the case of nanocrystals. Okay. So the question. Yes.
Make sure that I understand this. When you make those plots, you're taking that differential transmission signal at t equals 0, and that's what you plot there?
I'm taking the ratio of the transient absorption signal divided by the slow background.
So you're saying that the number of excitons correlate, or biexitons correlates with the differential transmission or absorption.
If you have one exciton, so essentially you have 1 unit in the transient absorption response. If you have 2, you bleach the lowest transition twice.
It's a linear
twice
relationship
as
to
much,
bleaching.
of course. But if you account for the distribution, the case Poissonian statistics is becoming more complex. The analysis of carrier multiplication data is actually easy. I don't have time to go into details, but the fact is, some people wondering why I'm using just linear relationship, why I do not see the saturation. I'm not supposed to see saturation in this case. Okay. So the question is, can I try to approach to achieve this ultimate 2 energy gap limit using some other material? Some materials which actually have even a stronger difference between electron hole masses than cadmium selenide. One such material will be in the maximum, where you have this very strong difference, 20-fold difference between electron hole masses. In this case, we expect to get actually to this 2 energy gap limit. These are very recent unpublished data where showing again quantum efficiency versus the pump photon energy for 3 different samples, and I don't have time to discuss this data, which actually are quite interesting, but for these nanocrystals, we actually activate the effect at this ultimate 2 energy gap limit. Okay, I have like 5 minutes. I wanted to talk a little bit about the distribution of carriers in this case. It's a very interesting issue. I'm going to spend maybe a couple of minutes on that. I said it's not Poisson. What is it? I actually can get a very good idea what kind of distribution I have based on very simple consideration, energy conservation plus the measured efficiency. What is interesting, based on energy conservation, the number of multiplicities is limited in the case of carrier multiplication because I cannot produce more excitons than is allowed by the ratio of the pump photon energy and the energy gap. I'm introducing the probability for different multiplicities. The sum of these probabilities is 1, but again, the number of multiplicities is limited by this value. Having multiplicities, I can define average multiplicity like that, so it's obvious. Now I have two equations, a set of two equations which I can try to solve in order to determine what are the probabilities for having different multiplicities. And of course, it's beneficial to look first at lower energies where I have the limited number of multiplicities. And fortunately, we have the activation of this effect slightly below the free energy gap. So I have the effect where I can only have single excitons and biexcitons. When I'm below free energy gap, I cannot produce three excitons. Okay, so I have just two simple equations. So I have the P1 plus P2 is 1, and then I define the multiplicity like that, and I know according to my experimental data, it's a linear dependence. Now, look at these very simple expressions. Okay, I start producing multi-excitons. What does it mean? Okay, I start to increase P2, but the sum of P2 and P1 is 1. That means immediately that I decrease the probability of producing single excitons, because their sum is 1. So I have interdependence between probabilities, and that's why my distribution is not Poisson. Because Poisson distribution is a direct consequence of having independent probability for having different multiplicities. Okay, now I'm crossing this 3G limit. Potentially, I can produce three excitons, but based on the dynamics which I measure, I don't see tri-excitons, meaning that even in this case, I only have single excitons. And biexcitons, that further means the increase in the multiplicity occurs at the expense of generating more biexcitons, but that further means that the probability of having single excitons drops down until it reaches 0. Very interesting. So if there is a certain energy, then each absorbed photon produces only biexcitons, nothing else. I'm creating a multi-excitonic ensemble with a single multiplicity. And actually, I can follow this dependence until I start to producing 7 excitons for each spectral energy. I only have 2 dominant multiplicities. Okay, and there are certain spectral energies when I produce a pure, clean multi-excitonic ensemble, all nanocrystals excited with 3 excitons, or all nanocrystals excited with 5 excitons. So it's a very remarkable observation. So it actually gives us now new opportunities for studying multi-exciton effects in nanocrystals when this data is not going to be complicated by the distribution of the multiplicities in the ensemble. Okay, I don't know if I have a couple of minutes to talk a little bit about the mechanism, okay? As I said, we don't have right now a picture which would be accepted by everybody, although I think I know how it works, okay? But people, not everybody will agree with me. Okay, so in bulk semiconductors, this process, multiplication of carriers occurs with impactonization, okay? And in this case, it's very easy to determine how their energy of creation of a single electron-hole pair will be determined on different factors. And this factor would be the energy gap, okay, the kinetic energy of carriers, which are left after impactonization event, and of course losses to phonons. Okay, based on energy and momentum conservation, you can obtain that the average kinetic energy of carriers produced by impactonization is close to 2 energy gaps, and of course there are some phonon losses, and this is how you arrive at this expression, the free energy gap rule. So the electron-hole creation energy is at least 3 energy gaps or greater in the case of infrared materials where you have significant contribution to the EG from the phonon losses. Let's analyze the data for semiconductor nanocrystals, okay? So if the same rule applied to calculating the electron-hole creation energy, okay? So based on the fact that we observe the electron-hole creation energy exactly equal to energy gap, immediately tell us, in this case, the process occurs without phonon losses, okay? And phonon loss has been a significant complication in theoretical treatments of impactonization in the case of bulk materials. It looks like, in this case, we can disregard phonon losses. And here, how we arrive at the simple model which we describe in this paper. I don't have much time to go into that. The model of direct photogeneration of biexcitons from single photons, okay? And you can explain this process using simple second-order perturbation theory, where you first create a virtual exciton using electron-photon coupling term, and then you scatter this single exciton into the manifold of the biexcitonic states using the Hamiltonian of carrier or exciton to biexciton coupling. Simple model, but it gives you a good idea about actually relevant parameters. And one of those relevant parameters is the strength of the exciton to the bi-exciton coupling. But there is another important parameter, and this is actually the density of state factor, which greatly increases the efficiency of the effect. This is the density of states from bi-excitons, and this is the density of states of resonant single exciton states. While this quantity, I have a coupling divided by the broadening of the single excitonic transition, may be small, but these numbers can be very big. And actually it's shown by recent calculations by Alex Zunger and co-work in this paper that the scaling with the energy of the density of the bi-excitonic state is really fast. It changes the fifth power of this excess energy above the lowest bi-excitonic state, while the density of states for single excitons changes linear. Okay? Because of this factor, I think the efficiency of the effect is extremely large. And there will be some other models that are posing in such efforts because some model which essentially is a limiting case of the model which we described in 2005 paper. They actually never recognized that in their publication, but I discussed it at the APS meeting. I don't have time to do that right now. A little bit, maybe just one slide regarding the implications of this effect for real photovoltaic devices. So first, it's expected to increase the power conversion efficiencies of real solar cells. In the case if there is no carrier multiplication, the limit, as determined by Schottky quasar, is about 31%, which is achieved at the optimal energy gap of about 1 electron volt. Now you take the real data which we observe for quantum efficiencies in less than night, you plug in into detailed balance calculations. And it's actually, okay, I don't have a reference. I published that in last year in the APL. Okay, so you can get that increase in the case of less than nanocrystals is not very significant. It actually goes up to 36%, from 31% to 36%, and the reason is obvious. So you have a very high activation threshold for carrier multiplication for energy gaps. In order to get high increase, you need to use materials with the early activation threshold. And such material can be, for example, in the marsenite, as I said. In this case, you can actually get 42% with the optimal energy gap, about 0.6 electron volt. And this number is actually interesting. This number is quite large. If you consider the fact that you're getting this number, or close to this number, if you approximate the quantum efficiency by the ideal state case I was showing, so using actually efficiencies which we see in nanocrystals, we can actually approach the ultimate limit for photovoltaic single junction devices, okay, defined by energy conservation. And I would like just to put this acknowledgement slide. So a lot of credit goes to Richard Schaller, who actually has been doing a lot of spectroscopic work studying this effect. Samples for carrier multiplication, different types of lead selenide, lead sulfide nanocrystals, indium arsenide nanocrystals, were fabricated by Jeff Petraga. And Milan Sikora is working on trying to implement this process in photovoltaic structures and in photocatalytic devices. And thank you for your attention, and sorry for being a little bit late.
We have time for a couple questions. Sure.
Yeah, you described the whole multi-phonon or multi-exciton process, kind of using the band diagram with a kind of one electron pitcher. But I'm wondering if you have a multi-excitons in a small nanocrystal, where now you have essentially multiple excited charges. The single electron pitcher, the band gap, no longer looks out. Is there any band gap effects associated with having so many carriers in a very small, confined nanocrystal?
Okay, I'm not sure if I understand the effect, but basically what is the influence of the specific band structure on the efficiency of the effect? Okay, and I think actually in case of let's say selenide nanocrystals, we have very favorable situation. You have a lot of very degenerate states. So you have 4 equivalent minima, okay, spin degeneracy. Plus, if you accurately perform the calculations, turned out that the states are equidistant in both conduction and valence band. And that increases the multiplicity. And then I was talking about the efficiency, okay? I actually mentioned the importance of this density of state factor right here. Okay, and this factor turns out to be extremely high, where right now in the process of actually publishing a paper, okay, where I directly calculate the degeneracy factors at certain spectral energies for lead selenide. And we see with a very small axis above the threshold for carrier multiplication, this factor can be 1,000. Okay, and it significantly contributed by this interesting band structure of flat solenoid, because you have a lot of highly degenerate states.
Given that you have many excitons, eventually you need to create a better and separate charges.
Yeah.
How much time do you have for that?
Yeah. Thank you, Mark. Have a slide. which I didn't have time to show.
Not know that.
All right. So that's, of course, the big question. You create these multiple charges. Now you're dealing with this problem of a recombination. So they recombine very fast, also because you have this very strong Coulombic coupling. How to extract the charges fast? So what we tried recently, so we put complexes, ruthenium complexes, on the surface of the quantum dots, and these complexes, based on the energy diagram, were supposed to take holes from nanocrystals. Okay, and we performed the usual time result experiments, looking at time result PL with femtosecond resolution, and we see the appearance of the fast component in the case when we have a complex sitting on the quantum dot, and the time constant is 5 picosecond, approximately 10 times faster than energy recombination. So it looks like, yes, we can extract charges faster than energy recombination. Thank you.
Let's take the last question here.
Yeah, I was thinking of John's question. So if you have many extons, can be an electron hole plasma too, or what?
Okay. If you look, the electron hole plasma effects are very pronounced in box semiconductors, right? So we know about this low energy shift, which we see in the case of box semiconductors. These effects are much smaller in the nanocrystal. Why? I was talking about that, okay? We have reduced dielectric screening. We have reduced dynamic screening. Because in bulk, essentially, you have these mobile carriers which can move adjust to the environment, which screen very efficiently excitonic effects, right? We don't have this type of effects here because carriers are essentially mobile. So their position is fixed by the rigid boundary conditions. Therefore, the plasma effects are extremely weak. We don't see very strong shifts of electronic states until even if we put 100 electron hole pairs per nanocrystal. Effectively, that would correspond to carrier densities up to 10 to 21. Okay, so the plasma effects are reduced.
And also you don't know exchange band narrowing? That's not important?
We see very strong exchange effects. We can talk about that. Exchange effects are enhanced because exchange effect scale is 1 over R cubed. And we see very strong electron hole exchange.
Well, let's thank Victor again and move to the next step.